Hello, welcome to the Advanced Synthetic Aperture Radar webinar series. My name is Erica Podest and I'm a scientist in the Earth Science Division at NASA's Jet Propulsion Laboratory, also known as JPL. I'm also an instructor for the NASA ARSET program. This is the first of a 4-part webinar series, and the prerequisite for this webinar is the NASA ARSET Introduction to SAR webinar series from last year, which covered the basic concepts of SAR, including polarimetry and interferometry. This webinar series will be primarily focused on applications, providing some background material on basic SAR concepts related to each application, but heavily focused on demonstrations. The webinars will cover land cover mapping, flood mapping, crop mapping, and assessment of surface deformation from an earthquake. I will be the instructor for today's webinar and the second one on August 9th. The third webinar on crop mapping will be covered by Dr. Heather McNairn from Agriculture and Agri-Food Canada on August 14th. And the last webinar on interferometric SAR for earthquakes will be covered by Dr. Eric Fielding from JPL on August 16th. Each webinar will be done in both Spanish and English. The Spanish webinars will all be at 1400 UTC, and the English ones will be at 2200 UTC on the same day. The presentations and the recordings will be posted online in a couple of days. So the learning objectives. I expect that by the end of today's webinar, you'll be able to understand the advantages of SAR over optical systems for mapping land cover, as well as what you can and cannot do with SAR versus optical. You'll understand the information content in SAR images relevant to different land cover characteristics. You'll understand the limitations of SAR for mapping land cover. You'll understand the optimal SAR sensor parameters for land cover mapping. And finally, through the demonstration at the end, you'll learn how to generate a land cover map from SAR. Here, we have a list of the advantages and disadvantages of radar remote sensing over optical. Two of the greatest advantages of radar over optical is that since radar is an active system, meaning that it provides its own illumination, it can observe the surface of the Earth during either day or night conditions. The other great advantage is that radar observations can be done under almost any type of weather condition, making radar particularly useful in areas that are constantly cloud covered, such as the tropics. Also, the radar signal can penetrate through the vegetation canopy or soil, while optical only sees the very top of the canopy or exposed soil. In addition, with radar remote sensing, there are minimal to no atmospheric effects or corrections needed, as opposed to optical where atmospheric corrections are critical for proper image interpretation. Finally, radar is very sensitive to the dielectric properties of the surface and to structure, whereas optical is sensitive to the spectral reflectance signatures of the surface. Of course, there are also disadvantages, and that is that the information content in radar data is different than optical, and sometimes difficult to interpret. Also, for radar images, the presence of speckle, which is that salt and pepper effect, makes it difficult to not only interpret the image, but it may increase measurement uncertainty and result in low classification accuracy. Application of a speckle filter is required in most cases. Finally, the presence of topography introduces distortions which need to be accounted for. And as a final comment, historic SAR images tend to have low temporal repeat. By that I mean on the order of 40 plus days, making the availability of dense time series images scarce. However, this is changing with Sentinel-1A and B, which together have a 6-day temporal repeat. So the main difference between optical and radar for land cover mapping is that optical is sensitive to the spectral properties of the vegetation and soil, while radar is sensitive to the structure and the dielectric properties of the vegetation and soil. And when I say structure, I mean size, density, and orientation of the target comparable to the size of the radar wavelength. Remember, it's wavelength dependent. When I say dielectric, I'm referring to the amount of water within the medium and whether that water is in a frozen or liquid state. So radar is essentially sensitive to the bulk of the vegetation or biomass, to the geometry of the vegetation, and to the dielectric of the vegetation and soil, which is closely linked to water content. So in essence, the information provided by radar is different than that provided by optical sensors. With optical, you can get things like NDVI or enhanced vegetation indices as indicators of vegetation health, while with radar you cannot. Another difference is that with optical, data is available from visible to infrared wavelengths consisting of several bands of data, which can offer different information on land cover characteristics based on spectral reflectance. With radar, the signal is typically only at one wavelength and one or two polarizations, so you don't have numerous data layers in radar. Multiple bands of SAR backscatter can be composed of multiple polarizations, which can provide insight into the scattering mechanisms of the scattering elements within the surface. The last difference is that optical sensors only see surface tops because the canopy blocks whatever's underneath. This limits characterizing land cover unless the characteristics of the top of the canopy are correlated well with what is underneath. With radar, the signal can penetrate through the canopy, depending on wavelength, and provide information on the vegetation and soil below, as well as information as to whether there is inundation present. There are a number of applications for using radar for land cover mapping and monitoring, such as mapping forests, wetlands, biomass, monitoring disturbance from fire or selective logging, or monitoring change such as deforestation or reforestation. There are many other applications beyond these. In the second webinar session, we will cover the use of radar for mapping wetland inundation, and the third webinar session will cover mapping crops. I will start out by refreshing your memory on the radar signal interaction with the surface. This figure illustrates the different backscattering mechanisms, starting with the one on the far left, which is specular scattering, which appears when there is a smooth surface, like a mirror, such as a water surface, and the signal scatters away from the satellite. The result is a dark pixel in the image. The next one is rough scattering, which results when there's some level of roughness on the surface, causing the signal to scatter in different directions, but mostly away from the satellite. As the surface gets rougher, as shown in the next figure, the larger the signal scattered back to the satellite. The next signal interaction is volume scattering, which occurs when the signal is scattered in multiple directions within a volume or medium. In the case of vegetation, the signal can scatter from multiple components, such as branches, stems, leaves, trunks, or the soil. I'll talk more about this further on. The final backscatter mechanism is called double bounce, which results when two smooth surfaces create a right angle that deflects the incoming radar signal off both surfaces, such that most of the energy is returned to the sensor. These areas appear very bright in the image. Double bounce is commonly seen in urban areas and flooded vegetation. Here we have an example of the radar signal interaction with the land surface. This is a pulsar L-band image at HH polarization over a site in the tropics. The brightest returns, especially along the river, are driven by inundated vegetation. The light gray areas are forests, and the dark areas are either water or deforestation, with different levels of regrowth. The larger the amount of biomass in regrowth areas, the brighter the tone. Note that deforested areas are very dark, similar to open water, and this can be a source of confusion when running a classification. In the next following slides, I would talk about the parameters that influence the characteristics of the signal. These are radar parameters and surface parameters. I'll discuss these in the context of land cover mapping, starting with the radar parameters. There are three radar instrument parameters that influence the transmission characteristics of the signal. These are wavelength, polarization, and incidence angle. The first radar parameter that we'll talk about is wavelength, and as you already know from the Introduction to SAR series from last year, in radar remote sensing we often talk about wavelength rather than frequency. This is because the length of the wave defines the interaction of the signal with the surface or medium. The wavelength is the length of the peak of one wave to the peak of the next wave, and it is inversely related to the frequency. So the higher the frequency, the shorter the wavelength, and vice versa. The table on the right lists the common wavelength bands in radar. Note that a C-band sensor has a wavelength of around 6 centimeters, while an L-band sensor has a wavelength of around 24 centimeters, and P-band on the order of 68 centimeters, which is a vast difference between them. There are two things to remember about wavelength. The first is that the longer the wavelength, the greater the penetration through the medium. And the second is that the length of the wave will determine the interaction with the surface objects. The wave will interact with objects that are approximately its size. The figure on the left shows the extent of penetration through different mediums with different bands. In vegetated areas, X-band is generally governed by the top of the canopy. C-band penetrates further, and L-band tends to penetrate deeply into the vegetation. Likewise, in the case of a dry, bare soil, X-band only sees the top of the surface, while L-band penetrates into the soil or deeper into the soil. Also, the wetter the soil, the less the penetration. There is a preferred wavelength depending on the type of study that you are conducting. The table on the right lists some of these. For example, P-band is good for studies involving penetration through high biomass forests, such as those found in the tropics, and for assessing biomass. It also penetrates deeper into soils and is good for assessing soil moisture at deeper layers than that provided by shorter wavelengths. L-band is also a good sensor for forest studies. C-band and X-band are better for agricultural studies. Ku-band and Ka-band for snow cover studies and glaciology. Ideally, for vegetation studies, the best sensors are P and L-band. There is currently no operational, freely available L-band data, and there is no P-band sensor in space. However, in 2021, NISAR will be launched, which is a joint NASA and Indian Space Agency L-band and S-band satellite. Also in 2021, the European Space Agency will launch Biomass, which is a P-band sensor. Here we have an example of penetration depth through vegetation with two different wavelengths, and this is in Kalimantan, Indonesia. The top image is a C-band image, which has a wavelength of about 6 centimeters, and the bottom image is a P-band on the order of 68 centimeters. These are false color composites of HH, HV, and VV. You can clearly see greater detail in the P-band image. The purple colored area in the C-band image is likely an area of low vegetation with patches of higher vegetation in between. So those green patches. In the P-band image, you can see that there's more sensitivity to the patches in between this area. South of the low vegetated area is a forested area with lower biomass than the area immediately west of it. These areas are more distinctive in the P-band image than in the C-band. Also to note are the purplish areas north of the river in the P-band image, which are areas having different forest structure or biomass. Finally, note the road structure in the forest area in the P-band image. You can't see these roads in the C-band image. The other radar parameter is polarization, which refers to the plane of propagation of the electric field of the signal, which can be in the horizontal plane or H plane, or in the vertical plane or V plane. Irrespective of wavelength, radar signals can be transmitted and or received in different modes of polarization. There can be 4 combinations of both transmit and receive polarizations, which are HH, VV, HV, and VH. Polarization is useful in providing information on structure orientation. Penetration depth is also influenced by polarization. In forests, HH tends to penetrate deeper into the canopy because it tends to be less attenuated than VV. HV is more sensitive to volume scattering and is hence a good indicator of vegetation cover. This is an example of a fully quad-pole L-band SAR system called UAV SAR, which is a JPL airborne sensor. In 2013, it acquired imagery over the Pacaya-Samiria Natural Reserve in the Peruvian Amazon. This reserve is a vast wetland ecosystem. And here we see a subset of that reserve. The images in black and white are HH, VV, and HV polarizations. Note that there is a river running through the middle. Also note the difference in intensity between the different images, especially between the cross-pole and the co-polarized images. The area east of the river is higher in HV than HH or VV. And this is because this area is a forest with higher biomass, and the degree of inhomogeneity of a surface or volume tends to depolarize the signal, meaning the polarization is changed, causing a high return in the crosspole in HV in areas where there is predominantly volume scattering, such as forests. Here you can see an RGB image of the different polarizations for Pacaya-Samiria. So HH is in the red channel, HV is in the green channel, and VV is in the blue channel. False color images are an ideal way to visualize the information content of the different polarizations through color combinations. You can see the information content that is unique to each polarization, and in this case is representative of different types of wetland vegetation. HV is in the green channel, and anything that is green means that the return is higher in HV than VV or HH. Likewise, anything that is red means that the return is higher in HH than in any of the other two channels. Anything that is magenta means that there is a similar contribution between HH and VV. The final radar parameter for discussion is incidence angle, which is the angle between the direction of the incident wave and the Earth's surface plane. In radar, the incidence angle increases across the swath from the near to the far range. So the area closest to the satellite is the near range, and you will find smaller incidence angles than the area furthest from the satellite or the far range. Low or small incidence angles will result in greater penetration through the medium and higher backscatter than large incidence angles. Large angles, on the other hand, will be more sensitive to surface roughness and will penetrate less into the medium. In this example, the top figure shows the effect of incidence angle in vegetation. A small incidence angle will result in the signal penetrating through the forest and the backscatter being a combination of components from the canopy, the trunk, and the ground, while a large incidence angle results in a combination of primarily the canopy and trunks, but not the ground. For forestry, the use of low incidence angles enhances the sensitivity to biomass, whereas the use of high incidence angles enhances the discrimination of forest types through interaction with forest structure. The bottom figure is an example with lower biomass vegetation, in this case a wheat crop. The return signal will be primarily from the soil and subsoil at low incidence angles, while at large incidence angles, the signal will be a combination of wheat and soil. Finally, regarding topography, slopes facing towards the radar will have small local incidence angles, causing relatively strong backscattering to the sensor, which results in a bright toned appearance in the image. So here's an example of the effect of incidence angle variation. On the left is a Sentinel-1 VV image, and on the right is the incidence angle variation for this image. The radar is right looking. Note that as we move across the swath from near to far range, the image becomes increasingly darker in tone, around a 3 to 5 dB difference in backscatter. If you measure, for example, the same forest at different incidence angles, then the measured backscatter will be different, even if there has been no physical change in the forest. Every surface feature will have a backscatter that is a function of incidence angle, so you need to be careful when comparing backscatter of a feature when there is a large variation in incidence angle. Incidence angle can especially affect the appearance of smooth targets on the image. Smooth surfaces can appear brighter than rough surfaces at small incidence angle, usually less than 20 to 25 degrees. Also, since smaller incidence angles are better able to penetrate vegetation, they are better for detecting flooded vegetation. Up to this point, we discussed the radar parameters that affect the signal as related to land cover. Now, I will discuss the surface parameters that influence the signal, which are dielectric and structure. There are three parameters related to structure: size relative to wavelength, orientation, and density. The length of the wave will determine the interaction with the surface objects. Size relative to wavelength defines the surface roughness, which refers to the average height variations in the surface cover from a plane surface and is measured on the order of centimeters. A surface is considered smooth if the height variations are much smaller than the radar wavelength. As mentioned earlier, the darker the pixel, the smoother the surface in relation to the wavelength. As the surface roughness increases, the backscatter intensity will become higher. In volume scattering, size relative to wavelength determines the components within the volume that the signal interacts with, such as leaves, stems, branches, or trunks in the case of vegetation. Orientation influences the interaction of the waves that are either horizontally or vertically polarized. And the density of the scatterers, or the biomass in the case of vegetation, will also influence the strength of the signal, in general making for a stronger signal when there is greater biomass. Here we have an illustration of size in relation to wavelength. If an object or surface roughness is the approximate size of a wave, then there will be interaction and there will be energy scattered back. Backscatter from vegetation is strongly dependent on the size of the scattering elements within the canopy. This example shows just that. It's an Austrian pine. The primary scatterers in vegetation are its components, such as leaves or needles, branches, stems, or trunks, with the size on the order of the wavelength. Scattering will also be dependent on orientation, and if it is similar to that of the incoming signal polarization. I'll talk more about that in the following slide. So here, for example, at X band, which has a wavelength of about 3 centimeters, the signal will primarily interact with the needles and small stems. At L band, the signal will primarily interact with branches, long stems, and the trunk. And at P band, the signal will primarily interact with the branches and the trunk. Also remember that the longer the wavelength, the greater the penetration through the vegetation. So at X band, the signal is dominated by canopy scattering, while at L band and P band, there are contributions from the vegetation and the soil. The soil contribution is even greater at P band. One more thing to keep in mind is that elements smaller than the wavelength produce little backscatter but can attenuate the signal. Orientation of the scatterers will influence the scattering response in each polarization. Let's consider a very simple example of vegetation consisting of just short vertical scatterers over a rough surface. Assuming that the scatterers act as short vertical dipoles, then incident horizontally polarized microwave energy will not interact with the vertical dipoles and will scatter from the surface underneath. Conversely, vertically polarized microwave energy will strongly interact with the dipoles. This figure shows the interaction of a horizontally and vertically polarized wave and their scattering intensity for different vegetation components. The left shows a short wave interaction, say X or C band, with two leaves. The leaf on the far left has components that are primarily oriented in the vertical orientation, and therefore scattering is greater in that polarization, while the leaf on the right is about equally distributed in the vertical and horizontal directions, and hence the scattering is about the same in both polarizations. The interaction with the trees at the right is with longer wavelengths, such as L band. The crown in the first tree is dominated by vertical scatterers, and the crown in the second tree is dominated by horizontal scatterers. The trunk is dominated by vertical scattering in both cases. This is a very simplistic figure to illustrate the concept. However, a forest is very complex, and what happens is that there is lots of volume scattering, meaning that the signal scatters multiple times from one component to the other. When this happens, oftentimes the signal is depolarized, and the cross-polarized return, meaning HV or VH, is larger than the co-polarized return. In general, depolarization occurs mostly over vegetation and hardly over open ground or specular reflectors. Cross-polarization is very sensitive to vegetation parameters. So HV is sensitive to volume scattering and is good for mapping different types of structure, forest structure. HH penetrates deeper through the vegetation and is good for looking at soil moisture because it has a stronger soil component. This figure illustrates all of the possible scattering mechanisms within a forest. Direct scattering from the tree trunks, crown-ground or ground-crown scattering, direct scattering from the soil surface, trunk-ground and ground-trunk scattering, and crown-volume scattering. Radars have the capability of monitoring variations in forest biomass. The relationship between vegetation biomass and radar backscatter intensity is nonlinear, as you can see in these graphs. As the vegetation biomass goes up, this relationship levels off, it saturates, and quantifying forest attributes loses efficacy in dense vegetation. The longer wavelengths, such as L and P bands, and the HV polarization, are most sensitive to above-ground biomass. The capability to map biomass is not consistent among different forest types. There have been many studies assessing biomass sensitivity for different ecosystems, and they have found that saturation levels vary with the type and structure of forests. Studies have reported that saturation occurred in biomass ranges of 80 to 150 tons per hectare for savanna forests, 40 to 150 tons per hectare for boreal and temperate forests, 97 and 270 tons per hectare for HH and HV polarization respectively for dense forests, 40 to 150 tons per hectare in the tropics, and 150 tons per hectare for mangrove forests. The other surface parameter that impacts the radar signal is the surface dielectric constant, which is controlled by the amount of moisture content in the vegetation and soil. Dry, naturally occurring materials have a dielectric of around 3 to 8, while liquid water is around 40 to 80. It's frequency dependent. So the greater the moisture content generally results in greater reflectivity and image brightness of the radar signal, which means that there is less penetration through the soil or vegetation. For example, surfaces such as soil and vegetation cover will appear brighter when they are wet than when they are dry. The lower the dielectric constant, the more incident energy is absorbed and the darker the object will appear on the image. This is an example of the differences in image brightness for different landscape dielectric values. The dielectric of frozen water is very low, on the order of 3, compared to liquid water, which is around 80. In the northern high latitudes, when the land surface transitions from frozen to thawed conditions in the spring, there is a large change in dielectric, and consequently a change in signal intensity from dark to bright. And this example shows that. This is a multi-temporal time series of an area near Fairbanks, Alaska, from the JRS-1 satellite, which was a Japanese satellite that carried an L-band sensor back in the 1990s. You can see that in February, when the land surface was frozen, the image is darker than in June when the land surface was thawed. In freeze-thaw studies that utilize radar signals, dielectric is the controlling mechanism causing changes in backscatter behavior. Similarly, in the tropics, the amount of water content in the vegetation and the soil will have an influence in the penetration depth of the signal and the reflectivity. You can especially see a large difference in signal intensity immediately after a heavy rain. Finally, the last thing I want to remind you about are the geometric distortions due to topography that are commonly found in radar images. Here we have two examples of distortions, which are layover and foreshortening. Layover occurs when the radar beam reaches the top of a tall feature before it reaches the base, resulting in the top of the feature being displaced towards the radar from its true position on the ground and laying over the base of the feature. Layover is most severe for small incidence angles at the near range of a swath and in mountainous terrain. Foreshortening occurs when the radar beam reaches the base of a tall feature that's tilted towards the radar before it reaches the top. Because the radar measures distance in the slant range, that's the slope from A to B, the image will appear compressed, and the length of the slope will be represented incorrectly. That's A prime to B prime. So depending on the angle of the hillside or mountain slope in relation to the incidence angle of the radar beam, the severity of foreshortening will vary. These distortions can complicate SAR-derived land cover classifications. In severe cases, the layover and shadowing produced by mountainous terrain makes classification inappropriate. In less severe cases, ancillary digital elevation data can be used to generate approximate corrections for terrain effects prior to classification. The final effect that topography can have on the signal is shadowing, which occurs when the radar beam is not able to illuminate the ground surface. Shadows occur behind vertical features or slopes with steep sides. Since the radar beam does not illuminate the surface, shadowed regions will appear dark on an image because no energy is available to be scattered back. As incidence angle increases from near to far range, so will shadow effects as the radar beam looks more and more obliquely at a surface. There are ways to correct for shadows through interpolation. However, I personally prefer to leave the shadow areas as areas of data gaps rather than use interpolated values. One final thing to consider when doing a land cover classification is speckle, which is the salt and pepper appearance of radar images. In order to reduce the speckle effect, you need to apply a filter, which will reduce the resolution of your image. Therefore, keep in mind that with radar, images might be given or stated to have a given a certain resolution. However, after applying a filter on an individual image, the spatial resolution of that image will be lower. SAR datasets have improved significantly in the last couple of years, and this list shows the legacy, current, and future SAR datasets. The ones with the green box indicate that the data are freely available, which you can access through either the Alaska Satellite Facility or the European Space Agency's Copernicus Hub. Note that the legacy datasets start with CSAT in 1978, which was an L-band sensor that flew for only a couple of months. During the 1990s, there was JRS-1 and ERS-1 and 2 going into the 2000s with ENVISAT, ALOS-1, and RADARSAT-1. Currently, there are a number of SAR satellites in orbit with Tandem-X, which is an X-band radar satellite from the German Aerospace Center, RADARSAT-2, which is C-band from the Canadian Space Agency, Cosmos SkyMed, which is an Italian X-band SAR, Sentinel-1, which is a European Space Agency SAR operating in C-band, and finally PAS-SAR, which is a Spanish SAR operating at X-band. There are future satellites coming up with SALCOM, which is an Argentinian SAR operating, or which will operate at L-band, and there is also the RADARSAT constellation, which will operate at C-band. NISAR is a NASA Indian Space Agency L-band and S-band sensor to be launched in 2021, and Biomass is a European Space Agency P-band sensor also to be launched in 2021. So it's very exciting times ahead for those people that are using radar in their research and applications. And this chart shows current and future satellites grouped according to bands, and the far right indicates their repeat cycle. Note that they have repeat cycles of just a few days, which allows for a constant monitoring capability. I want to briefly touch on NISAR, which is a NASA and Indian Space Agency satellite that will launch in 2021 and will operate at L and S bands. It will have 3 to 10 meter resolution depending on its mode of operation. And it will provide repeated observations which will allow for applications such as ecosystem, hazard, and disaster monitoring that include ecosystem disturbances, ice sheet collapse, and natural hazards such as earthquakes, volcanoes, and landslides. Next, I will show a demo on land cover mapping using the Sentinel-1 toolbox and L-band data from ALOS-1, which is data that is freely available and can be accessed through the Alaska Satellite Facility data portal. And what we'll do here is I'll walk you through the different steps to generate a land cover classification. And to do this, we'll be using data from the ALOS Pulsar satellite. This was a satellite that operated between 2006 and 2011, and it was a satellite from the Japanese Space Agency. It had an L-band sensor, and it had different polarization. So I'll talk a little bit about the different modes of operation. So the data are freely available, and you can access the data through the Alaska Satellite Facility. So do a Google search for the Alaska Satellite Facility, and you'll come up to this main page that you're seeing here. Go to Datasets, click on Datasets, and you'll see a window pop up with a list of all of the different datasets that you can access through the Alaska Satellite Facility. However, since we're interested in ALOS Pulsar, let's click on that one. And it will take us to a page where there's more information about ALOS Pulsar. Here's the global coverage. And here are some links for more information about Pulsar data. There's some documents and tools, and the radiometrically terrain corrected products. I'll talk a bit more about that. So let's just start with the search and click here, Find Pulsar Data. This will take us to the search engine, the Alaska Satellite Facility search engine, which is called Vertex. And up pops a window that says how we want to perform our data search, either geographic search, a granular search, or a mission search. What we'll do is we'll select geographic search. And down here, there's a little window that pops up that wants to guide us through the whole process. But I'll dismiss that because I'll walk you through the process. So this is a very easy page to use, search engine to use. And what we'll do, the first thing we need to do is specify our geographic region of interest. And I've selected an area that is near the city of Manaus in Brazil. So Manaus is around here, and this area is southeast of the city of Manaus. And so I'll just draw my box over our area of interest right there. And the next option here on the left is to specify the dates. We'll leave those as is. And finally, you have to specify the data sets. So the default is Sentinel-1 data, and we'll deselect those and select ALOS Pulsar. So we hit search, and the search is usually very quick. And so on the right side is a list of all of the images that have some level of overlap over our area of interest. Okay, now Pulsar data has different modes of operation. One is called the fine beam single mode. That means it's got one polarization, usually HH, or it could be BB as well. Then there's fine beam dual pole, two polarizations, and that's HH, HV, or VV, VH, depends. And within the different modes, there's also one called PLR, which has 4 different polarizations. And so the image I've selected for this demo is an image that has 4 polarizations. So let's narrow our list of hits. So we have 335 hits. Let's narrow those down to PLR. And we'll scroll down to the image that I have selected, which is this one here. So click on the thumbtack, and up pops another window that has an RGB image, a small RGB quick look image of our area of interest. And just by seeing this small quick look image, you can see that this area has a lot of variability. I'll talk a little bit about what we're seeing here when I open the actual image, but in general, it has water, it's got some flooding, some deforested areas, forested areas. So here on the left, you've got specifics relating to this image. And so the date of acquisition is April 11th, 2007. PLR mode, ascending or descending orbit. So this is an ascending orbit. And something that's important for you to remember is that whenever you are doing any type of analysis where you're using 2 or more images, you should never combine the ascending images with the descending images, just because the viewing geometry is different. So do your analysis with just the descending images, and then do a separate analysis with the ascending images, and you can compare the results, the products that you've generated, but don't combine the raw images into your analysis. Okay, and then what we have here are the different images available. So we've got these two. The ones that we're interested in are the terrain corrected, and we've got 2 options: high res terrain corrected and low res terrain corrected. Now, with radar, and those of you that have seen the introduction to SAR webinar that we did last year, there are a series of pre-processing steps that are needed to be applied to radar images before you can start classifying the image. So you need to do a radiometric calibration, and you need to do a geometric calibration on the data, and then you can really then use that data to run classifications on it. So what the Alaska Satellite Facility has done is that they have terrain corrected the data. So they have done the radiometric and the terrain correction. So they're radiometrically terrain corrected, and the high-res data sets are at 12.5 meters, and the low-res data sets are at 30 meters. Now, only the ALOS PAL-SAR data sets have been RTC, radiometrically terrain corrected, and not all of them. So if you do a search and you come up with the specific information for that image that does not have this, it means that you need to deal with the level 1.5 image, and you need to do a radiometric and geometric correction on the image. All right, so let's download this image. And I have a login already, and I have the image on my folder, but you need to log into the system or create or register into the system. Again, this is free, but you do need to register. All right, so once you have the image, you need to unzip it. And I'm opening here the unzipped folder. And inside the folder, there are a couple of different images. Actually, these I've created. I should have deleted these. But all of these on down are the ones that the original images that come in that zip file. And so you've got the 4 polarizations. You've got the DM that was used to correct these images. You've got an RGB image, quick look image. You've got a KMZ file, so you can overlay this on Google Earth. And so what we'll do now is we'll open Snap and open the images. All right, so we'll go to Snap. We'll do File, Open Product. And we'll go to that folder and select our images, okay? And I missed the HH, it's right here. Okay, so now it's always good practice to open the bands, to visualize the bands that you've loaded up, because sometimes there are issues with the bands. They might have errors in them, they might have banding, they might not have been fully processed correctly. So you want to take a look at them and make sure that they look okay before you run all of these different things on them. Okay. Okay, so they all look okay. And one thing I wanted to show you is, so we've got HV, VV, VH. So this one is HV, and this one is VH. So I'll toggle between these two. And these images are not exactly the same, but they're essentially the same. And so what we'll do in order to better manage our different bands is just close the VH image. Okay, so go select the name, right click, and then close product. And that leaves us with these 3 images. Now, in order to run a classification or do any kind of really processing or analysis on the Sentinel toolbox, you need to have the images in the same file. So that's the next step. We will go ahead and stack these images. So go to Radar, Co-Registration, Stack Tools, and then Create Stack. And then you load up the images that you've opened, and there they are. And I want to change the order here so that HH is on the top, then we have HV and VV. Okay, so you go to the next window, and it says Create Stack. We need to change one parameter in there. It says Initial Offset Method. We change that from orbit to product geolocation. That means it uses the geolocation information of the images to stack them. And then finally, write. So you specify the name, and the Sentinel toolbox adds on the name of the process onto the image file. So it's taking the name of that first file in the list, and it's adding on stack so that we can identify which image this is or which file this is. All right. And then here you specify the directory. So we'll hit run, and I have this already, but I will do another one. I'll overwrite it. It's very quick. All right. So here in our window on the bottom, anytime you run anything, any new process, the new image will appear at the bottom. So here we have that new stacked file. And if you open bands, you've got the 3 images. So you've got HH, you've got HV, and you've got VV. Okay. So let's do an RGB of this, just to visualize all 3 polarizations together. And to do that, you select the file name and you right-click, and you say Open RGB Image Window. So that's an RGB. And basically what we're seeing in this image is, so these areas of very low backscatter in the HV image, those are areas where it's a smooth surface. So probably those areas have no vegetation. And then you see some areas here with some level of intermediate backscatter. Those areas are areas where you probably have some sort of secondary regrowth. And then over here, you have some effects of topography. And you can see that better in the HH image. So you see these areas here, you have some brightness. And it's always kind of a sanity check, a good sanity check to compare things to Google Earth if you're not familiar with the site, if you don't have any site data. And so that's the case here in terms of, I've never been to this area. So let's take a look. We're zooming in, and so this area here is this area right here. And you can see that pattern a little better here with the HV. So you can see that there is topography in this area, right? And the reason that you see that brightness is probably because there's topography, and it's bare. It's a bare mountaintop. Okay. So, all right. So the next thing that we want to do is, in radar, usually you talk about dB. So that's backscatter. You represent that as decibels. And so the next thing we want to do is we want to, let's see, convert these to decibels. Okay, I'm not getting the option. Okay, I'm sorry. Let's go back. Before we convert it to decibels, let's do something here first. Let's
apply a filter. For some reason, I'm not getting the option. So let's apply a filter, and let's apply a radar filter to remove speckle. So one of the things that's very obvious in this image is the presence of speckle, and that's really, it comes with radar, right? You've got speckle that you have to deal with. So you have to apply a speckle filter, and you go to radar speckle filtering, single speckle filter, and you specify which image you want the filter applied, and the name of the new image will have SPK at the end. Okay, so processing parameters, so we want these 3 bands, and I encourage you to explore the different speckle filters available. Here you have a list of a number of different filters, and what we'll do today is we'll select the Lee filter, and box size is very important. So the larger the box size, the more speckle you get rid of, basically. And so, but the greater the resolution loss as well. So remember, the resolution, the original resolution of this image was 12.5 meters. And if you apply a 9 by 9 box, your resolution is going to be about 112 meters. So let's run this. And you'll see a really large difference between the image without the speckle and the image with speckle. If you leave the speckle there, it's just going to, you'll see it in the final classification. Okay, so let's do this. Okay. So there. So let me open, and I'll tile these horizontally so you can see the difference. There's a way in the Sentinel toolbox to see these images side by side. So let's do window, tile horizontally. And then what you do is you need to link the windows down here and there. So this is the same image. This one is the non-filtered, and this is the filtered one. Okay. So we will. All right. So now you want to convert these to a dB. Okay, and the way you do that is you select that specific file name, you right-click, and you have an option that says linear to dB. And it says it will convert it into a new virtual band. You say yes. Linear to dB, yes. And then linear to dB. And you say yes. Now, one thing is, it is a virtual band, so that means it's stored in memory. And what you want to do is actually save it as part of this file. And to do that, you will right-click, and say Convert Band. And you see that V here disappears. So right-click, Convert Band, and then right-click, Convert Band. And there you go. So let's view our images. In dB. So, all right, there. So it looks a little bright and washed out, and what we need to do, this is the HH. What we need to do is we need to play around with the histogram. So we go to the second window down at the bottom, and go to Color Manipulation, select the editor, Basic, there, Sliders, and excuse me. So you select sliders, you select the histogram, and you'll see it's always good to look at the histograms of the images just to see the distribution of the values in the image. First of all, you can see that the max value for HH is 5.97, min value is minus 23 dB. And so you've got 2 humps here. This one, this lower one, that's clearly water. and this is everything else. So let's just change this and do like that. And let's take a look at the next one, and we'll do the same. This is HV. Look at the values. The max value is minus 6.8, and the min value is minus 29. And again, water is clearly very discernible from everything else. But this distribution does look different. You do have a larger dynamic range in the values as compared to HV. To HH. Okay. And then we'll do the same for the last one, which is VV. And same thing, water is way out there. We'll just bring this closer and okay. So let's create an RGB of those dB images. Let's open RGB and okay, so it looks a little washed out again. Yeah, sometimes you need to adjust the histogram. Okay. All right around there. Okay. So one thing that I pointed out earlier is the intensity levels between the different images is different, and with HV there's these areas where there's low vegetation or no vegetation are more discernible than with HH. And so what helps sometimes is to do image ratios, and what image ratios gives you is kind of, it maximizes the information content between two images, right? So what we'll do is we'll create a band math here of the image ratio of HH to HV, and we'll edit this expression, and we'll say HH is the first minus HV. And the reason we're doing minus is, remember, these the dB images are a logarithmic. They're non-linear. So in order to go from the original image to dB, it's the 10 log 10. And so whenever you're doing mathematical manipulations with non-linear numbers, then to generate a ratio, you actually subtract the values. If you were doing this ratio on the original images, then you would actually do the division. Okay, and we'll say okay. So this is the ratio, and what's popping out here are really the areas where HB is low. So all of these bright areas is where HB is very low. Okay, and another thing is this new ratio is virtual. It's a virtual image. So let's do linear 2 from dB. Oh, sorry. Let's do a convert band to save it there. All right. So the next step is let's do a classification. Now there are generally two types of classifications, right? There's unsupervised and there's supervised. And the Sentinel toolbox actually has a nice selection of supervised classifiers. Of the ones on the list, you can explore different ones and compare your results, but random forest tends to give really good results. The one thing about supervised classification is that you do need to train your classes. So we'll go ahead and train our classes. So that would be the truth. You need to train the classifier and let it know what the statistics of your classes looks like. So in order to do that, we'll go to vector, new vector data container, and we'll say water. That'll be the first one, okay? And so what we'll do is we then go up here to rectangle drawing tool, and we make a box over the area where we know there's water, okay? And here, if you take a look at water throughout the image, so you've got water here and here, it's all really, really dark. But there might be cases where your water varies in intensity, because sometimes there might be wind and it might change the surface roughness of water. So it might not look as dark uniformly throughout the image. And you want to make sure that you characterize this and that you select training areas over the areas where the water is really dark and where it's not so dark. All right, so that's our first class. Then we'll select the second class and we'll call that forest. And we'll go up here and select forest, okay? And let's do another class and we'll call this non-forest. And non-forest areas are these areas that are very dark. They have very dark backscatter. And you can always we can always do a okay, so okay, so we'll select all right, and then we'll define another one and we'll call it non-forest topography. And so these are the non-forested areas where you have the effect of topography. All right, and then we'll go ahead and we'll select a new one and we'll call this regrowth. So these are the areas where there's some level of vegetation, and you can see this very nicely in the HV. So it's these areas here where there's some level of vegetation. So okay, and then finally, the last class I want to define is flooded vegetation. Flooded vegetation. And those are these areas down here by the river. All right. So now what we do is we go to raster classification and select supervised classification. Select random forest classifier, and we will then load up, add all of the images that we've opened, and we need to specify which one we want to run the classification on. So we want to run it on the speckled, the filter, the stack that where the filter has been applied. So I will remove all of these. Okay. And this is the one we want to use. And then here's a list of our classes. I'm not sure why geometry is appearing there, but these are the classes that I defined. And then down here is a list of all of the images within this file, and we just want to use the dB ones and the ratio. And so you write this, and so let's say, and it could take a little while to run, depending on your computer and depending on the size of the image. But early on in the process, you get a window that pops up that gives you an accuracy assessment on how well each class was classified. And so water, it looks like water was great, very easy to classify. And then the other classes, and this is all based on the training areas, right? And so remember, the quality of your classification is very much based on the quality of your training classes. So we got forests, non-forest, non-forest topography, so you can use this as a measure of how well your results are. Okay, and I'll just wait for this to run. And the result will be not only a classification image, but along with it comes like a confidence image. So it tells you the confidence in classifying each of the classes. So this is the classification, and then this is the confidence image. All right, so this is our result, our resulting classification, and what we'll do is we'll change the colors to make them a little more realistic. So we'll go to color manipulation, and we'll change water to blue, forest to green, non-forest to red, non-forest topography to red as well. Regrowth, we'll leave that as dark green, and then flooded vegetation, let's just make that magenta. So that's our result, and let's compare it now with our RGB image. Just tile them side by side. You go to Window, Tile horizontally, and leave the screens. And so you can see that generally the areas where you see the pink in the RGB, which are areas of deforestation, they are picked up as red here in the image. The areas of regrowth that we had identified, like these areas, this area here, that's picked up in the image to a certain extent. Okay. And then the water, that's great. Then the flooded vegetation, that was picked up very nicely, actually. You can see it here between the river channels and over here and even over here in these areas. And then the forest was picked up as well, but the issue is it is speckly, it is noisy, this image. And you can go back and, for example, apply a larger filter or a different filter, or you can also refine your classes. Let's see, one thing that you can do to clean this up a little bit is to apply another filter to it. So you select label classes and you go to raster, filtered band, and you apply a median 3x3 filter. And so we'll go here to the color manipulation table, editor, and we want to display the range, the data. We have 6 classes, so it goes from 0 to 5. And then we'll have colors, and we will then go to table and assign colors, right? So the black is, what's black is water, so we'll assign that as blue. Our class 1 is forest, we'll assign that as green. Our class 2 is non-forest. Our class 3 is also non-forest. Our class 4 is regrowth, and we'll just assign a dark green to that. And then our class 5 is flooded vegetation, actually. Okay, flooded vegetation. So let's do a horizontal tile there. And compare. And you can see that, you know, applying that filter on the classification does help clean things up. Okay, so with that, that concludes this demo. But I just want to throw out there that there are many, many different things you can do when classifying, and you can explore different things. You can, as I mentioned, you can explore the use of different filters. You can explore the use of different information layers. Like, for example, you can use a DM in your stack of images. You can also use textures, and you can explore what sort of information they can provide. Sometimes they help separate classes. Actually, there's a whole suite of textures in the Sentinel toolbox. If you go to raster, image analysis, texture analysis, here, and go to processing parameters, there's a whole list of textures, and you can play around with the type of information that they provide. Some give you information about how homogeneous your pixels are within the window that you define. So window size is very important, right? Or how inhomogeneous they are, or what's the variance of the pixels, or what's the skewness. So there's a lot here to play with that you can explore and see if it actually helps in your classification results. So with that, thank you very much for your attention, and I am open to your questions now. All right. So does dielectric work in vegetation? The answer is yes. So the dielectric properties, the amount of water in vegetation has an impact on the signal, right? So the larger the water content in the vegetation, the less the penetration of the signal through the vegetation, and the higher the reflectance. What's the accuracy level of radar for vegetation carbon stock and biomass estimation? So for biomass estimation, I read a list of different biomass estimations. It varies very much depending on whether they're forests in the northern high latitudes, boreal forests, or tropical forests. And so kind of the rule of thumb for L-band is 100 tons per hectare in the tropics. Could be totally off, but isn't ERS 1 or 2 and MBSAT now free? It's possible that they are free. You should check with the Alaska Satellite Facility. I think ERS 1 and 2, you need to submit a request to access the data, and there's some requisites that you need to meet. But I encourage you to check. How can I use SAR to map the damage caused by armyworms in maize? Okay, so this depends on how large the damage is, okay, and how big your plants are. So what radar provides us is information about, remember, structure and the dielectric properties of the surface. So structure, with maize, for example, what you can do with radar is see how the biomass changes with time, right? How your crop is growing with time, and see whether there is a change that is not related to the natural growth that you are seeing in other areas of your field, for example. And that might be then, the cause of that might be because of armyworms. So the biomass in the area where the armyworms are affecting the crop are areas where the biomass would be lower, assuming it's that large of an effect, that it's basically eating the leaves out. What is the polarization suitable for flood monitoring in case of urban and non-urban? Okay, so with urban, it's very difficult to look at flooding in actual urban areas because urban areas have very high backscatter because there's double bounce, right? So it's the same mechanism as in flooded vegetation. So an urban area, you've got roads and you've got vertical structures, which are buildings. And when urban areas are flooded, you've got a water surface instead of a road, and you still have the vertical structures. So the areas are still going to be very bright. You can monitor flooding in urban areas that have natural environments, like, for example, golf courses. There might be open water in golf courses, or, for example, the prairie urban areas, so areas in the vicinity of urban areas that are flooded, or parks that are flooded. You can see that sort of thing. All right. And there was also a urban flooding webinar that was done recently that you might want to visit. Some researchers use polarization ratio as example, HV over VV. How does it affect classification? So what it does, it helps maximize the information content between two images, right? So you might have an information content unique to one polarization and unique to another one. So when you do these ratios, you're really kind of maximizing this information content, and you can help better classifiers or identify certain classes. I guess it's just being observant of the order you put them in during the stacking tool. Yeah, that was just me. You can put them in any order, but I like to have HV in the green channel because HV, it naturally, when you do an RGB, if you have HV in the green channel, then the forest will appear green, which is, it makes sense to what we're used to. And the reason HV appears green, or pops out in the green channel, is because you've got depolarization. You've got a lot of volume scattering going on in forests. And so the cross pole is better at detecting that. After running the stack tool, how do we know the band order? That's a good question. Actually, you can either make note of it, or you can, let's see, there's a way to change the name when running the tool. So let's do stack tools, create stack, and so let's do this. Uh, yeah, actually, I thought there was a way you could change the name, but it seems like you'll just have to remember what you placed in each band. Okay, so the next question. Which images do you use for band ratios? Usually you want to use the images that have the greatest contrast. So you want to use like HH over HV or VV over HV, and these are things that you can play around with. Which algorithm of supervised classification? I'm not sure I understand that question. How can I use Sentinel-1 data for mapping wildfire scars? That's a good question, and it was brought up in the first session today. So if you send me an email, I'd be happy to send you a list of publications that show you how to use Sentinel for wildfire scars. So those scars, same as you saw here, deforestation, you'll see that scars are also very dark in the images. And they can be identified. What is the resolution of the ALOS pulsar radar image? It's 12.5 meters, the original resolution that we downloaded. Which polarization is better for crop classification in different cropping seasons? Which polarization is used for agriculture crop classification? That's a good question for the third seminar. Is going to cover just that. What are the optimal polarizations for crop classification? What band is appropriate to map oil spill on water bodies? That's a really good one. And so that's been done, actually, to look at oil spills. And the reason you can use radar to look at oil spills is because the area that is covered by oil, the water that has oil on it, has a smoother surface than the water that doesn't have oil on it. So especially if you're out in the ocean, and you normally have a little bit of wind, so the water that doesn't have oil gets ruffled up a little bit, has some sort of some surface roughness, while the water with oil appears very smooth, and it's really easy to differentiate them. The best polarizations, so you saw that HV is very good at just identifying water, but that's not going to give you the difference between water with oil and water without oil. So the best ones would be probably VV and then HH. What format basically SAR data is stored as TIFF or CIOS? Okay, that's a great question. These were TIFF. Other images in the Alaska Satellite Facility come as CIOS images. Others come as HDF, so it just depends. And by the way, you can download these images. For example, if you, so let's just close this. If you right-click on the image and you say Export View as Image, you select Full Scene, Full Resolution, and down here there's a GeoTIFF option. You can export it. Okay. Or you can also, there's an option here where you can export your files into other formats. So there's all of these other formats, if your software of choice is QGIS or something else. All right, so next question. Since for urban homogeneity, which data is very useful? Since for urban, I'm not sure I understand this question, but what I think this person is asking is, like, how can you classify urban areas? If you have urban areas where there's no flooding around it, then it's the areas that have very bright, very, very high backscatter. If you have an urban area where there's flooding around it, like Manaus, for example, then in my experience, textures have really helped. And there was one in particular called energy, which gives you a measure of how homogeneous your pixels are within your window. And that helped separate or better separate urban areas from flooded areas, because urban areas, I noticed, tended to be a little more homogeneous than the flooded areas. Can I determine a land-water boundary beneath a marshland? Low vegetation without trees? Yes, yes, you can. You'll definitely see that. How does one separate fallow land and vegetation with water class in Sentinel-1 SAR? Fallow, okay, that's a really good one. And that's really a source of confusion. And that's really where these ratios can really, really help. So you might want to try HH over HV ratio, or VV over VH, since Sentinel has a VV polarization. So areas that are fallow, smooth, have no vegetation, tend to be confused with water classes. The C-band can estimate biomass over dry green evergreen forest. Yeah, you can estimate biomass with C-band, definitely. The only thing is it's going to saturate at a lower level than with L-band. Can I use radar images to monitor landslides? Yes, you can. And actually, what the session that will be relevant to this is going to be the last session. That will be interferometry. So that session will cover looking at surface deformation as a result of an earthquake. But the techniques that will be covered are also applicable to looking at landslides. So you're looking at these really small movements of the surface, on the order of centimeters. Are there any free data sets of previous S-band satellites, particularly interested in S-band utility for ag monitoring? Not that I'm aware of. Not that I'm aware of. It's not common to have SAR S-band satellites. And so NISAR, which will be launched in 2021 that I talked about, has an S-band sensor. And that's around 12 centimeters. So you're better off using just C-band, Sentinel C-band data. Ooh, which polarization is better for glacier classification? Actually, I'm not sure about that one, since that's not really my field of work. But if you send me an email, I will send you a list of publications and I'll answer your question. What are the characteristics of drought-prone areas with respect to radar images? Drought-prone areas, okay. So I'm not sure what the specific of this question. Like, for example, what comes to mind is there is a satellite in space. It's a NASA satellite called SMAP, the Soil Moisture Active Passive, and it measures soil moisture globally. And so you can, every 3 days, by the way, at 9-kilometer resolution. And for drought-prone areas, you can take this product, the soil moisture product, and see how the soil moisture is changing as an indicator of potential drought. Question 24. Since the dielectric constant which influences the backscatter, what will this mean for someone assessing or estimating the soil organic carbon across different land use? And can this be related to Landsat 8 data, land surface temperature of in relation to its soil moisture freestyle and SC and the NDVI to the GPP? Wow, that is one very loaded question. All right, so let me try to answer parts of this question. So the dielectric constant will have an influence on backscatter. Yeah, definitely. Primarily when you have like extremes. For example, in the northern high latitudes, when it's frozen and it's thawed, there's a great difference in the dielectric. So you're going to have much darker images when the surface is frozen as when it's thawed. If you're estimating soil organic carbon, that is very tough, okay, for different land use. I'm not sure how you're estimating soil organic carbon, whether you're thinking of using radar to estimate soil organic carbon. It's not clear to me. But if you are using radar, you need to use some sort of model, right? And you would need to account for the moisture in the soil, because if the scattering properties are going to be different whether your soil is wet or whether it's dry. And by the way, this SMAP has a soil organic carbon. So it has what's called a level 4 product, and that is a model product to estimate and net ecosystem exchange. And one of the variables that it's also estimating is soil organic carbon. What sort of return times can we expect from the satellites being launched in the next few years? It's a really great question. What sort of return times? And I think there was a, in the presentation, there was a graph that indicated, one of the last slides in the presentation indicated the return times. But it's on the order of a week and a half to 2 weeks. Is there any data to show the elevation of SAR data? Okay, so I think what this question is can you generate a digital elevation model from SAR data? And the answer is yes, you can through interferometric SAR, and you need at least 2 images. What radar data, and that might be a topic that we'll cover in a future SAR webinar. What radar data are most appropriate for the study of soil moisture? Okay, for the study of soil moisture, it's L-band, definitely. One, because it has greater penetration through vegetation, and so you're more likely to be sensitive to soil, and 2, because it does penetrate soil a little deeper. And so SMAP is measuring soil moisture at about 5 centimeters. But that kind of varies. The wetter the soil, the less penetration you have. And P-band, in fact, if you have something like P-band, you can go even deeper. And that's really where soil moisture is important, at the root zone level. So really, the longer the wavelength, I think the better it is for studies of soil moisture. Do we have to perform histogram equalization while classifying the images? No, you don't. That was just for visualization. But sometimes it helps to equalize the histogram to better see the images and see the dynamic range of the image, and then to be able to better select your training classes. Is it possible to measure the height of urban structures using radar imagery? Not that I'm aware of. I think the best bet for measuring the height of urban structures is LiDAR. Can these snap processes can be automated for? Yes, they can actually. And let me show you here. So they do have a batch mode, and you go up here, it says batch processing. So basically this graph builder, you create a sequence of steps that you want to apply on your images, and then you do the batch processing. Okay, let's see. Do you advise combining SAR images with optical images for land cover mapping? Yes, actually. You can try. These data sets are complementary. The information content in radar is different from optical. And if you have an area that might be difficult to classify, like, for example, you have just areas where you have very low backscatter because they're deforested, or they're just very smooth surfaces and they're being confused with water, sometimes optical really helps to separate those areas. Can SAR be used in identifying salt-affected soils? So salt changes the dielectric of the soils, right, and of water. Can it be used to identify salt-affected soils? If they're very salt-affected, I think they can. I'd have to look through the literature. But SAR or radar has been used, for example, look at salinity in the oceans, so sea surface salinity. And that is related in part to the dielectric properties. Can we use Sentinel images to map paleo channels? So Sentinel images are a bit more limited in their penetration, but you might be able to map paleo channels indirectly. through what's on top. So the vegetation on top of paleochannels might differ from the surrounding vegetation, and you might be able to classify these different types of vegetations. Can SAR images be used to model effect of river linking project and other development projects like dams? Yes, I don't see why not. Can SAR I'm not sure exactly what sort of issues you are interested in, but yes, you should be able to see the difference in a river before and after a dam. Okay, so it seems like that's it for the questions. So with that, I'll end today's webinar. Please make sure to tune in to the next one, which is on Thursday, and we will cover flood mapping for that one. The following one, the third one, will be on crop and soil mapping, and then the fourth one will be on August, let's see, 16th, and that will be on interferometric SAR, looking at surface deformation. So thanks everyone for tuning in. Thanks for your attention, and I'll see you, or I'll hear from you on the next one coming up. Thank you very much.